The first question says, using the band gaps of silicon and gallium arsenide, plots the relation of intrinsic carrier concentration versus temperature, hence determine the concentration of phosphorus that will be sufficient to make GAs eccentric extrinsic at 700 degrees Celsius. So the first thing I did is I equated the intrinsic carrier concentration of silicon and GAs at 300 Kelvin. Then I found our A, which is the mass. Using that, I derived an equation to find each intrinsic carrier concentration at different temperatures. This is the table I used. So for 100 degrees Celsius, we have 373 Kelvin. We have this carrier concentration. Using this equation to derive it. So then after that, I plotted my graph. This graph is not exactly correct since I used 1 times 10 to the power 2, 1 times 10 to the power 4, 1 times 10 to the power 6, 1 times 10 to the power 8, and 1 times 10 to the power 10. In real life, in using real programming language like MATLAB, Python, you won't be able to derive something like this exactly because they will have to range from 0 to 1 times 10 raised to the power 1, then 1 times 10 raised to the power 2, which would be very big. So I created this using Word document, and this is the graph for gallium arsenide and silicon. Second question says, determine the concentration of phosphorus that will be sufficient to make GAS extrinsic at 700 degrees Celsius. Extrinsic simply means that our concentration will be far greater than the intrinsic carrier concentration. So I multiplied it by 10 raised to the power 2. This should be the minimum concentration that will make GAS extrinsic. Next question says, using the datasheet. I don't have the datasheet picture here, but I'll explain what I did. If you find the noise margins, this is noise margin low and the noise margin high. Noise margin low is subtracting the input low minus the output low, because the input low is greater than the output low, and the noise margin high is subtracting the output high minus the input high. These are my values, and this is my graph here. The switching points are here when that's at the least input. That's when it turns on, because it's an inverter. Zero input to give us higher, and a lower input to give us an higher output. So at the low point it switches on, and at the high point it switches off. The second question, derive the sizing ratio of NMOS and PMOS for the inverter. So basically I use the formula in the formula sheet. This one right here. Hey, what time I even did this now? This question 2 and 3 can be gotten from the formula from the formula sheet. This is the formula for the C input and the C output. If we add them, they become the C total. But I was asked to find the C input and the C output. So we have this, we have this. This fourth question, sorry, says sketch the input output pulse passing through the inverter showing propagation delay approximations. So here, this is the input curve. This is when it goes from low to high, and this is when it comes from high to low, Right here, this distance here is the propagation delay. This is the propagation delay. Now, since this is the input signal, this is the output signal. For the output signal, we have a curve here because it's not exactly a smooth signal. We have a curve here. The 50% of this, going to the 50% of this, gives us our propagation delay from high to low, and from low to high here, and from high to low here. This camera is not working, so you don't see my face. And the last question. If you want to increase the noise margin low, sketch the inverter cross section to achieve that. To increase the noise margin low is the same thing. We're using a formula to get this. So we are basically increasing this value. To increase this value, we have to increase Kp over Kn. That's and we have the formula for this. We have the formula for this. So from here, we know that increasing Kp, we have to increase the width of this one. We have to increase the width and reduce the length. And for Kn, since it is Kp over Kn, we have to increase this width. No, we have to decrease this width and increase this length. So that's what we did here. This is the width. We increase this and we increase this. P must be greater than Pn to increase the value for the noise margin low.